Cool. So I guess I got the mic. So hello, everyone. So to this last talk, I hope you are at least somewhat still ready. At least I can promise you there's going to be drinks and snacks afterwards, because in this talk there's going to be lots of code, so sorry about that. So my name is Christian. I'm from the Android team at MongoDB Realm. And today we're going to talk about coroutines and how they work in practice on Kotlin Multiplatform. So for those of you that don't know Realm, so we've been around for quite a while by now. We're an open source object database. So the database itself is written in C++, and then we have a number of language SDKs on top for most major mobile platforms, specifically for Android as well. And the genesis of this talk is basically that right now we are sort of rewriting that SDK to be Kotlin multi-platform compatible. And there we sort of learned a lot of things that I want to share with you today. But coroutines is a rather big topic, so we can't really dive into everything. So in this talk, we can look at like the shared code, we can look at the boundary between the shared code and the different platforms, or we can look at how we consume coroutines on the specific platforms. In this talk, I'm going to look into two areas specifically, mostly on the shared side, like how do we write coroutine-aware code when you have a multi-platform shared library, and then on the iOS side, like how do we actually interact with iOS, which doesn't have the concepts that coroutine or that Kotlin and coroutines has. So that means that in the shared section, we're going to look into how dispatchers work, because there are a lot of gotchas there. We're going to look into how the memory model sort of affects your coroutine code and what you have to be aware of. And then what we do about testing, because that differs also from what we do when you just have Android. And then on the iOS side, we're going to look into how we can map our coroutines and our flows into the Swift equivalents of which are completion handlers, their combined framework, and their new async await features they introduced this year. So if we start with coroutines in the shared code, then the first thing you basically have to decide is which kind of coroutine support you want. So if you just pick the default library from JetBrains, then you are getting the core library, which was written for the JVM. Unfortunately, that has a rather big limitation on if you're working in shared code, because the memory model there sort of freezes everything, and that sort of restricts you if you're writing code that needs to run on native. That restricts you to one thread, which is obviously a rather big limitation, since like most people, like the entire reason they want to use suspend functions is they want to move things to the background thread, and that simply stops working if you use the default library. So then they released this native MT library, or multi-threaded library, which basically lifts this restriction, but at the cost that it has more bugs right now. And they're still working on it. So their plan is that they want to merge these two, but right now there's two. We think we actually have a choice, but in reality we actually don't, because Ktor, which is the default network stack on multi-platform, basically ships with multi-threaded. So even if you try to avoid including it in your own libraries or your own code, I suspect like 100% of you are already including Ktor somewhere in your multi-platform stack. So that is basically the default choice. Fortunately enough for us, so like JetBrains are saying, I don't know how many of you saw the keynote yesterday, like they are working on this new memory model for native, so they are working on combining these two. But right now, so that means that this multi-threaded variable do become the standard, and that is sort of what I'm going from this talk. So if we go to the first topic for writing coroutine-aware code in the shared code, then the first thing you hit is sort of these dispatchers, which is like this model we have for moving things between threads. So if you come from Android, you probably have written code like this. So you have some sort of view scope, and then you sort of want to do a network request, then you want to do a network request, write that to the database, and then ship that back to the UI. And you would expect, OK, I should just be able to write similar code in the shared code, right? Because that's the entire reason why we want to share code. Unfortunately, this is sort of tricky, because the dispatchers on the JVM work rather differently from the dispatchers you have available in the common code. So if we take them one by one, so the unconfined dispatcher are available in both, and it basically means that we don't care which thread you run on. You just run on whatever thread you like run on when you started the suspend function. So this is available in common code as well, and well, it has its uses. Then we have the default dispatcher, which is somewhat tricky. So it's sort of being sold as this is the dispatcher you need to use if you want to do background work. And that sort of is also the way it works on the JVM, because there it's backed by a thread pool. Unfortunately, on native, it's backed only by a single thread, which obviously means that if you want to do parallelize work, you are going to run into performance issues. So it will work, but you will see issues there, right? And this is just something to be aware of. So this is also why I don't know how many of you remember ArcsJava. They had this computation scheduler, and this is basically what that is. So then they're sort of missing, so what about I/O work? So what about that? So unfortunately for us, on the JVM, they have an I/O dispatcher, which is backed by a thread pool, which is exactly what we need. But this one isn't available in common code. So that basically means that it's up to you to figure out, if you want to have like massive parallel tasks, it's up to yourself to sort of figure out how to do that through these dispatchers. JetBrains doesn't really do anything for us there. Then we have custom dispatchers, which is then obviously what we're going to use to bridge the gap of missing I/O dispatchers. Is then we have to use those to figure out some way of doing that. And then last, we have the main dispatcher, which runs your job on the main thread. And like we're used to that just working out of the box, at least on Android. Unfortunately, as soon as you hit multi-platform, that dispatcher has a lot of edge cases that makes it really dangerous to use, which we'll look a bit into. So if we take a look at the code we just saw before, right? You can see here we are starting a view scope on main, and I would like to, ideally, if I have this in my common code, I want to test this. So why couldn't I just write a test around this? Unfortunately, as soon as you do that, you run into two issues. One, if you run this code on iOS, it actually deadlocks because of how multi-platform interacts with the iOS dispatch queues. I don't know exactly what's going on, but it does some weird locking there, which means that it actually doesn't work. At the same time, like I would assume most of you, if you have a coroutine library or like a module, the way you run tests is that you want to run tests on the JVM, because running them as Android tests are just slow, so we want to do that faster, right? But if you do that and try to run it as a JVM test, you're basically hit by this exception saying, oh, we are missing a main thread, which is like true because the JVM doesn't have the concept of the main thread that exists on Android. So what do we do about that? So if you're writing for Android specifically, they have this Kotlin Coroutine test library, which is like pretty neat and has a lot of really nice functionality. Unfortunately, that doesn't exist in common. So this functionality of being allow you to sort of override which main dispatcher you have, which is what you do for Android, you would simply in your test say, okay, let me override the main dispatcher with my custom one. That doesn't exist. And similar to like run blocking tests and all of these nice features that exist, they simply aren't available. So we have to do something else. And if any of you care about this, I linked the Kotlin issue down there. Go upload that and make them port it to multi-platform, because we all want it. So that means that the only solution we actually have for like sort of manipulating these dispatchers in common code is that we have to write our own sort of injection points. So you might want to do this already just because you want to like give that control to the users. But actually, if you are doing it for multi-platform, there's really no way around it. So this is just one way of doing it, where you sort of just have an expect object that sort of have handles to dispatchers, and then depending on your platform or depending on what kind of code you're on, or if it's test code or not, you can sort of instantiate that the way you want. So in this case, I'm just using my custom threads for main and I/O. And then the code we had before, we just rewrite it to this, and then everything works. And most likely, if you want to give your users control of this anyway, you maybe have something similar, where this is user-provided dispatches. Let's see. So that means that's the first advice of this talk. Always, if you're writing for coroutines in the common code, always inject your dispatchers, because if you don't, it's going to hit you at some point. that brings us to the Kotlin native memory model, because that is going to hit us in a bunch of like really annoying places when you're writing coroutines. Even though you are using the multi-threaded library, we still have the native memory model to sort of contend with. So for example, this is a simple case I have where we are creating an object. Then we are sort of passing it through a context switch to do an update. And in that case, as soon as we do that, the object is frozen, and we are getting hit by this exception, right? So this works fine on the JVM, but as soon as you do it on native, you get this. So how do we get around this? So there are basically, there's a couple of solutions. So this is one of them, is that if you truly have an object that needs to be mutated instead of, like, that is one of the reasons data classes are really awesome, because they are immutable, and you don't like hit these memory constraints. But if you have like a model that does need to mutate, you can do something like this. So JetBrains provide this atomic foo library that basically you can expose things as atomic references, which does allow you to work with a memory model, so that if you want to do updates, then it's perfectly fine to freeze the object because you're just manipulating the object atomic references. So, and this actually do work. Another thing is that you want to code with this mental model of having things frozen. So instead of, as you saw before, like we only got hit by the frozen exception as soon as we sort of hit the boundary, and we don't know like when that happens. So you might want to already from the get-go consider all your public API classes as frozen. As soon as if there's a slightest chance that these objects are going to like cross a context switch somewhere, you're basically better off freezing these objects from the get-go, because then you sort of get errors as soon as possible. So this is just one way of doing it, where we do it in the constructor. So like users of the object doesn't have to do it. We can just do it in one central location. So that leaves us advice number 2. So basically, when you're writing code for the shared part of your library, basically you have to do that with the most restrictive memory model in mind. And then you might ask, so how is that possible? Because if you tried it, you know that common code, it has. So because it also have to work on JavaScript, which have entirely different restrictions, there's a lot of the functionality in the Kotlin native part of multi-platform that actually doesn't exist in common because it isn't supported on JavaScript. But if, like, I assume, so just out of curiosity, how many of you are writing multi-platform with JS involved as well? Not many. Oh, there's one there. So how many are doing it just with JavaScript, or so just Java and iOS? So a few more, right? So that is the common case. And if you have that, then it's easy to sort of just lift the APIs you need for the Kotlin memory model, lift them into the common code, and then you can sort of make a no-op implementation for the JVM, because like any code that works with the frozen memory model in mind also works for the JVM. So it's sort of safe to sort of like construct your code in a way that sort of works with the Kotlin native memory model, because we do know it works on the JVM. And we also know that so JetBrains just announced like they're going to make like the same memory model we have in JVM is going to like also exist on native, but they're still working on it, right? But they have said that once we get there, they will still maintain the old memory model. So that means that it's completely safe to code against something like this today, and then you'll have it working even when they switch. So let's see, this is actually, yes. So that brings us to testing. So when you sort of have to bridge this gap between your coroutine code and your suspend code, then we have this magical function called onBlocking, which basically sort of blocks until the suspend functions inside are done. And so on the surface, this is like a really magical method, and it does a lot of nice things for us. Unfortunately, it's also very easy to get into sort of deadlocks with this one. So this is just one example. So the documentation for onBlocking basically says you're not allowed to nest these because it could potentially be problematic. And yes, that is true. Unfortunately, writing code like this is actually rather easy if you have some sort of public API with a lot of entry points. And all of those entry points are sort of need to run blocking, and then these entry points might call each other internally. Then you can easily run into a situation like this. And then it becomes tricky to debug. So this one actually works just by accident, because in this case, these two run blocking calls are using different dispatchers. So they run on different threads, so they don't block each other. Unfortunately, you can't really guarantee that, right? Because especially if you have a platform where there might only exist one thread, like we just saw the default dispatcher on iOS is single-threaded, or or if it's user-defined, we don't know what they're going to put into our code. So for example, this, if we're using the same thread, it actually blocks on JVM. So that basically means that what do we do about that? And unfortunately, this case is super, super hard to detect. Basically, the output in your apps is going to look like they won't appear frozen, but they will just look like nothing is happening. And you won't actually get any hints about where it's wrong. So the only thing you can really do is to spin up your debugger, try to look at the stack trace, and then try to locate these waiting threads. So ideally, you have named your thread pools or whatever in a way so they sort of give a hint about what they're about. And then you can sort of see, OK, all of these waiting. If they are, you know you have this case somewhere. And then, unfortunately, it's just down to annoying debugging, because we won't get any hints anywhere for finding this. So advice number 3 for writing coroutine code, basically, you need to make sure that you can't make any assumption about your dispatchers. So you have to assume that all of them are basically running on the same thread, and you have to test that scenario. And the same thing you have to test on both JVM and native, because they have very drastically different behavior. So even though you might be running your daily workflow on JVM or on macOS, whatever you prefer, but if you don't test both on your CI, you are going to hit issues at some point. So to summarize the shared code, so basically always just assume you're using the native multi-threaded. So most likely you're doing it already, and it is going to be the new memory model anyway. Always inject your dispatchers. Avoid dispatchers.main at all costs. Fortunately, that's going to be easy if you're injecting them. Also assume that try to test a scenario where all your dispatchers run on the same thread. Again, that is going to be relatively easy if you have all your dispatchers being injected. And then finally, you have to keep in mind that if you're working against KMM or Kotlin Mobile Multiplatform, then there's actually a lot of methods there on both that exist on both native and JVM that doesn't exist in JavaScript, and we can lift those into our common code and use them there. There do exist like a few libraries already do supply some of these functionality. I know like TouchLab has a few of their stately libraries that does some of this for you. But in general, it's very little code you have to copy to do this. But it is something you have to do. And let's remember that the frozen memory model, it works also on the JVM. It actually, at least from our experience, if you code with that in mind, it actually allows to think about your code in a way that makes it more structured, that makes it less prone to race conditions. So even though it's annoying to work against, having to do it actually has, I think, huge benefits for your code. So that brings us to coroutines and how we then use them on iOS. So the default implementation that is applied from us from JetBrains is that they are exposing suspend functions as completion handlers. And that looks roughly like this. So for those of you that don't understand Swift, sorry, there's going to be a lot of Swift code on the next slides. But that is basically how a completion handler looks in Swift. It's basically like callback. If you envision a callback API in Kotlin, that is basically what this is. And it actually also works the same way. So the work is being done. So it doesn't have any sort of concept of threading. It just executes the work on whatever thread you sort of start again on. And that is obviously something that is slightly problematic, because like the entire point of having like suspend functions is that we want to control like where they run somehow. So how do we do that? Like if we try to do the naive approach, so Swift or iOS has this dispatch queue, a global dispatch queue that is a background thread or threads. Let's try to do the work there and see what happens. Then we get caught by this, which basically tells us that we are hitting the memory constraints of Kotlin Native. That doesn't allow us to share objects between threads. So it's a slightly different exception because on iOS, it can't freeze the methods the same way we do in the shared code. So basically, it just tells you you can't access objects across threads. OK, that should be easy to solve. But first, it also reminds us that if you have an API that is Kotlin Multiplatform aware, and there's the slightest chance that your objects are being visible on the Swift side, and those objects jump between threads, then you need to freeze them, basically. So we saw the methods before for doing that. Another option is also, so in this case, we sort of exposed a special method for it. But unfortunately, due to how Swift does generics, we have to cast the thing again. But now this actually allows us to freeze things from the Swift side. And if we do this, then we get hit by another exception. So fun. But this time, it actually just tells us whatever you're trying to do doesn't ever work because suspend functions can only be called from the main thread. So all our work was sort of couldn't really be used here. So basically, what we have to do instead is that if you want to control the threading where work run from the Swift side, it's basically impossible. You have to do it from the Kotlin side. And that sort of does make the Kotlin code slightly less idiomatic, because code like this you have here, where you sort of change the context inside the method, yes, it is possible to do that in Kotlin, but in most cases, this would something at outer scope would sort of define, right? But if you want to have some code that is shared between iOS and Java or Android, this is basically the pattern you have to adopt, that you have to find some sort of bridging mechanism where everything basically runs on the that the communication channel is basically on the main thread, but then all the threading concerns are being moved to Kotlin. So personally, I think that makes for a cleaner model as well, but like it can be annoying in cases. And if we see that now, things actually do work. It's starting on the main thread. Yeah, by the way, these thread identifiers, so Swift doesn't have, you can't name threads there, so we can only like pick up the native ID, so that's why it looks a bit weird. But you can see that, yes, the work is actually being called on the background thread while being returned on the main thread, which was what we were out for. And it looks idiomatic on the Swift side now, like it has just a completion handler, but it then turns slightly awkward on the Kotlin side. So basically, if you want to control threading, you have to do that in the shared code. But what about exceptions in these completion handlers? Let's say we have a method that suddenly throws an exception. Then, yay, yet another exception or a crash in our program. Because if you have any sort of Kotlin code that throws an exception, if you try to get that exception to Swift, you basically crashes the program because it needs to know exactly what kind of exceptions are being thrown. So that means that any public method you have, let's see, you are basically forced to annotate it with whatever exceptions you might throw, because then they can be exposed correctly on the Swift side. And that also means that your completion handlers now have to handle this in a way that looks roughly like this. So what about flows? So like suspend functions is just one use case of coroutines, right? But like in many cases, what you really have is sort of these flows, because if you have your immutable or you have your unidirectional data flow, you're listening to some view model that is just exposing things as flows. So ideally, we would like to just consume those flows from Swift. So one way of doing it is like this, where we're just calling the collect method directly, which is obviously looks like super annoying, which it also is, so I wouldn't recommend it. But it is possible to sort of implement the interface and call the correct methods and all of that. And even the consumption point looks a bit weird. Yes, we're calling collect, but we have to sort of do it like slightly awkward. Instead, so I picked this up from one of so JetBrains is the Kotlin Conf app. Basically, they're moving instead of exposing it as a flow directly, they're actually changing the semantics slightly. So instead of a flow, you actually just have callbacks that just looks roughly like a flow. So basically, what they're doing here is that you extend your flow type in the Kotlin side, then turn it into, it gets a callback method. It can trigger as many times as it needs, and then it actually exposes a closable on the Swift side that then is responsible for closing whatever scope you have on the Kotlin side. So this looks like roughly something like this. And you can see down there, I'm also freezing it so that the consumer side in Swift doesn't have to, it can basically consume this from anywhere. And then on the Swift side, it suddenly looks a lot nicer, because now we have this watch method we implemented, and it basically just consumes this data in a very natural way. And then we have this job as a closable. So that's sort of the unfortunate side. Then now we have a life cycle of this flow we have to deal with, which if you're just using Kotlin, that is sort of handled automatically by the scopes. But on Swift, we sort of have to do this manually. And this works as expected. But as you can see here, like there is no error reporting. What about threading here? Because as you saw, like everything is running on the same thread again. So how can we go about doing that? So if we try the same thing again, let's see what happens if we try to run this flow on a background thread. Does that have any impact? And so yes, it actually does. So you can see it, well, it doesn't. Yeah, it does and it doesn't. So the work itself it's doing something on the background thread, but like all the work are still being executed on the main thread. And the reason for that is, if you remember, let's see. Okay, this is slightly broken. If you remember the common flow implementation, we had this launch-in clause, which basically defines where you are running your coroutine, where the coroutine work or the flow work is doing, and that is being run on main right now. Obviously, we can then control this like inside the flow if we want to, and move it to other things. But this is slightly annoying, is that you can't really control where the flow is running without extra work. But if we do it like this, but I mean, you can sort of pass in. So I have seen people sort of, if they're doing this, you can give them a handle to some other scopes, and then you can reference them for iOS if you want. But it is going to be slightly complicated. So let's maybe just dump this. So what about error handling? So if we have something like this, a flow that throws in, let's see, I think nope. So if we start with a flow where something crashes from the Kotlin side, then you are seeing an exception like this, because it doesn't really handle, there wasn't any error handling on the Kotlin side, so that basically crashes Kotlin, which crashes Swift. So how can we work around this? Basically, we have to make sure to catch these exceptions in the common flow, because that is sort of the boundary where we convert flows to callback functions. So what we're doing here is that we are catching any sort of error coming in the flow, and then sending it into Swift as a callback. And that also means that we have to change the call side, where before we were just receiving data. That was easier. Now we sort of are forced to sort of change that to both send data and an error exception, and then your call side looks similar to what it did for completion handlers, is that you basically have to check for errors here. But that sort of does give us a working API for just consuming both suspend functions and flows directly in Swift, with the lowest amount of effort. But sometimes you might have use cases where you want to do further work on the platforms, and ideally on iOS we have the combined framework, which is basically just RxJava and flows for Apple devices. So it would be really nice if we could convert our flows to these combined publishers. So fortunately, John O'Reilly made a nice blog post about this. So I took his approach and generalized it a bit. So basically what we do is that we have to implement this publisher API on the Kotlin side, on the Swift side. And then we have to hook that into some way of consuming things in Kotlin. And basically, we take the same approach as we do with the completion handlers, where we sort of invoke callbacks. So in this case, we are creating this new subscribe method that sort of creates a callback for each sort of live event you can have in a flow, which is like event is being sent, or sorry, elements are being sent, the flow completed, or the flow failed. And then on the Kotlin side, we basically just have to implement these things and make sure that we catch these scenarios in the flow and make sure to dispatch them correctly. And if we do this, then we can actually get something that looks pretty reasonable on the Swift side. So like ideally, the listen to flow method here would have some sort of extension function just called a publisher. Unfortunately, due to the way Swift and Objective-C does generics, that isn't possible. So we are only left with, we have to like instantiate our own wrapper class, which we're doing here. But then for those of you that have written combined publishers before, this looks actually fairly idiomatic. So sync is basically collect, and store is a way to store the object that controls the flow, or the combined stream. And if we do this, then things work. Except that things, as you can see, everything is actually being sent and processed on the main thread, which like commonly isn't something you would do. You would want some way of controlling this. So how can we do that? Let's assume. So normally you would go to your like standard toolbox for your combine streams and say, okay, then we just subscribe on this dispatch queue global, which normally means, okay, whatever you do here, just do it on the background thread, and then send me the results once you're ready. Unfortunately, that sort of, and then you could do the work like this, just common like mapping things, like you could do more advanced work, and then like when you're done, close to being done, you continue on the main thread to sort of update the UI. Unfortunately, this doesn't really work. So as you can see here, you can see everything still happens on the main thread. And the reason it does this is that we sort of defined the scope in, we defined the scope of what the work in Kotlin side runs on the Kotlin side. So that means even if we do subscribe to the thing on, to the flow on the global dispatch queue, like that in itself doesn't really change threading. And unlike flows, like it doesn't affect downstream. So that means the map method here still just runs on whatever thread emitted the elements, which in this case was the main thread. So basically what we have to do is that as soon as, if we want to sort of do work on iOS on a different thread, than whatever was emitted from Swift, or sorry, from Kotlin, we basically, as soon as we receive elements from this Kotlin flow publisher, we basically have to move it to whatever thread we want to do it on. And a word of caution for those that have worked with iOS. So this dispatch queue global is super dangerous. I would never use that for like anything like this, because it's like a concurrent queue, so it doesn't guarantee ordering in any way. So even if your elements arrive in order, it doesn't guarantee that they're emitted in the same order. So you're basically forced to create your own queues to sort of do this. And this is obviously like boilerplate, like a Swift developer would like look at this and say, this looks, yes, it's possible, but it looks like slightly odd. But it does give us the power of changing from flows to a combined world where the Swift developer can then like use all the tools he wants there. And if we do this, then we can see that things do work correctly. So we are sending things from the main thread because that was how we defined the work to happen on the Kotlin side. But now all the mapping operations actually do happening on the background thread. And once that is done, we do receive them finally on the UI thread. So it can be updated there. But what about error handling? So basically, there are two cases. So one is what happens if combined throws an error, like here. Basically, what happens is that you can see that the publisher being canceled and then the failure being sent. And it seems like the flow on the last three elements here, that is the Kotlin side continuing to send elements. And that might look slightly odd because you just failed the entire thing, right? And the reason that happens is because a failure on the Swift side doesn't actually result in an automatic cancellation on the Kotlin side. We have to propagate that error, and we have to do that by manually canceling it. So this cancel method in the publisher or in the subscriber on the Swift side, it has like events you can hook into, but you still have to cancel on the Kotlin side, wait for the event loop on the Kotlin side to actually acknowledge that. And in the meantime, if you're like flow is fast enough, it can emit like all its elements. So in my case, it was just like an array of 3 strings. So it has done all of that before like it was notified about a failure. But we also saw that nothing actually got through on the Swift side. So even though Kotlin still keeps emitting, it is being handled correctly on Swift. So what happens then if something crashes in the Kotlin side? Let's say we have a flow like this. Basically, what we have to do now is that, if you remember before, like the failure case before was set to never. And now, in order for us to handle errors from Kotlin, we basically have to redefine the interface of the combine publisher so that it knows that an error can occur in this, because that forces the downstream, those that sort of subscribe to the publisher, they need to handle that case. So in this case, you can see here, we are now in the onFlow method. We are sort of wrapping this in a Swift error, and then we are marking the publisher as failed. And then on the consumer side, it basically looks like this. Now we have to sort of have this receive completion handler that people need to always implement, but then they can actually see errors coming from Kotlin. And if we try that, then it actually works as expected. The thing starts sending, then we crash the Kotlin side, then the publisher gets canceled on the Swift side, and the flow completes completely. So that brings us to the last sort of element to how to work with Swift. So the latest and greatest from Swift was async await, which is, if you squint, basically looks like suspend methods. So it would have been ideal if those worked like completely like async methods. So this support is still very experimental in Kotlin, and they basically said it can change with a note without warning. So use at your own risk. We did try it. So basically, a task is just like a scope in Kotlin. So what we do here is we create a task, then we call await on our suspend function, and then we see what happens. And hooray, more exceptions, because for some reason, these suspend functions or this support still only works on the main thread, which is like the entire point of using async await. It was that you could sort of do things on the background thread. So, and if you use a default task like here, that is like running in the background as a default. So if you want to use these async await APIs, you are basically forced to redelegate work back to the UI thread, which is done through this main actor annotation in Swift, which forces this method specifically to run on the main thread. And then we can sort of do it. But then it sort of turns into a roundabout way why even do it in the first place. But it is possible. And you can see here, it actually works as expected. But where it actually gets most interesting is around SwiftUI, because SwiftUI does have this extra task closure that does run on the UI thread. So that means that if you have suspend functions you want to expose to SwiftUI, then it suddenly turns easy, and it does run on the correct threads. You still have to like do the threading work on the Kotlin side, but the consumer side in SwiftUI is really neat, and then SwiftUI takes care of tearing this down correctly. So what did we learn about the IO setup? So basically, suspend functions are only callable for main, and you basically have to deal with that. So generally, I would say, depending on your architecture, that isn't as huge a deal as it sounds, because like I would still advocate if you think of the boundary between iOS and Android as only running on the main thread, this is actually a pretty nice architectural constraint that sort of forces you to push everything or as much as possible into Kotlin, which only leaves like the pure UI on the Swift side. So, but it's still something to keep in mind. Then another thing is that anything that can be exposed to Swift, you basically have to consider how can this fail, and then you have to mark it accordingly, because if you don't, your entire app is gone. Coroutine scopes are not controllable for Swift. Yes, you can sort of expose a variable that can sort of like, you can do some roundabout way where you can do it, but generally, coroutine scopes, you have to do that, all of that logic on the Swift side. But if you're going with the approach of moving as much as possible to the shared code, that isn't that big of a deal. Then all objects that are exposed in Swift, you should try to freeze them, because if you don't, you are going to get hit by something at some point. And yeah, so as we saw, Kotlin has like automatic support for these suspend functions, but we have much more control through these custom callbacks, where we can sort of define our own interfaces. We can sort of, do we want error handling or not, like all of these things. And more specifically, it also works on background threads. So I would say right now, if you want to do this sort of interop, like trying to go the custom callback route is probably the most flexible. And yeah, as we saw, like any sort of event in either suspend functions, like cancellation or errors, in both flows and suspend, they have to be moved manually. That nothing is being given to you. You have to do all of that yourself. So that brings us to the end of the talk. So like pretty much all I talked about today has been around constraints about the memory model, which fortunately JetBrains already acknowledged. Yes, it's painful to work with. Yes, we're going to fix it. So hopefully next year, none of what I said today matters a bit because they fixed everything. So, but at least for the next year, hopefully this is valuable. But yes, so this was it. So thank you for coming. Or any questions?